Hi everybody, this is Cal again with section 6.2, orthogonal sets. So, the definition of an orthogonal set is right here in the beginning of the section. That's one to know, that's one for the books. Example 1 is showing that a set is orthogonal. This is pretty basic. Now, theorem 4 is kind of interesting. Make sure you understand what that's saying. And think in your head about the picture, why this should be true. Remember, an orthogonal set is a set of vectors that are all orthogonal to each other. What are the angles between those vectors? What does that mean for linear independence? So, definition here is an orthogonal basis. It's about what you would think. It is a basis that is also an orthogonal set. Great. And then theorem 5 is a useful computational theorem for how to find the weights in a linear combination when the vectors that are in that combination are orthogonal to each other, or are an orthogonal basis for a subspace. Instead of sticking things into a matrix and row reducing, you have a nice little computational formula here. That's really nice. Example 2 shows that at work. Then we get into this idea of orthogonal projections. And the thing that you want is this picture over here, figure 2 on page 342. Do read the discussion, figure out how it's coming up with these things, although we will cover this in class. You want to know what an orthogonal projection is, what the component of y orthogonal to u is, figure out what y is, what u is in this picture. And an orthogonal projection onto a line, L, and how these things all differ. We do end up with a formula here which should sound familiar to theorem 5. Example 3 lets us play with it. And I would read and try to understand this geometric interpretation of theorem 5. Work through example 4 as well. It's useful and quick. Picture here again, very good picture for orthogonal projections. So do read this section, geometric interpretation of theorem 5. Decomposing a force into component forces. This is something you've done in other classes, and this is more just pointing that out. Finally, we get into orthonormal sets. Orthonormal set is an orthogonal set that is also normalized, length 1. An orthonormal basis is what you think it is. We have an example of, looking at an orthonormal basis. Finally, we have a theorem about matrices with orthonormal columns. This is going to be interesting. We'll get into this a little bit. And a theorem about how these matrices work with lengths and dot products and so on. It's not going to be immediately obvious from a first reading what's going on here or why this is useful. For now, it's something to read. When we're dealing with square matrices in that setting, an orthogonal matrix is a square invertible matrix U, so that U inverse is U transpose. You want to think of this as being a square matrix with orthonormal columns. And be aware that there is really bad notation here. Okay? An orthogonal matrix is a matrix with orthonormal columns. So be aware of that clash in nomenclature. Alright, so that's about it for this section. So have fun with it.